Now we're going to talk about imperfect sampling, or in other words, the impact of imprecise measurements and rounding error on the signal. To do that, we have to have a way of talking about noise. So how do we measure noise? Well, absolute values in sound rarely exist. You could just turn up the amplitude a little bit, you get louder sound, but you also get louder noise. And so the important thing usually is the ratio between the signal and the noise. That's called the signal to noise ratio. And the signal level itself is variable. We could be recording a very quiet sound or a very loud sound. And usually the signal to noise ratio is maximized by when you have the loudest sound compared to typically fixed noise. And so signal to noise ratio means the ratio between the maximum signal and the noise. The units for measuring signal and noise are decibel. The decibel is a logarithmic unit. Every 10 dB corresponds to a factor of 10 in power. 20 dB is 2 factors of 10, so that's a factor of 100 in power. And it turns out power is proportional to amplitude squared. So 20 dB is a factor of 10 in amplitude. 6 dB approximately is a factor of 2 in amplitude. Now, quantization noise is due to rounding. So we take the signal and round it to the nearest integer value when we have integer samples, which is standard, typically 16-bit samples, sometimes smaller, sometimes a little bigger. So let's think about the nature of rounding. If the signal is varying by quite a lot and the increments between samples is very small, which is typical, then on any given sample, where the signal falls between these integer sample values is random. And so we can think of the amount of rounding is just a random offset. And one way to think about it is the true signal is the rounded signal plus the rounding error. Okay, so the rounding error is essentially looks like noise. We assume that rounding is uniformly distributed from minus 0.5 to plus 0.5, and so we get a noise signal with an amplitude of 0.5. Here are some examples of quantization. This is, I have a sine tone and I have some actual music, and these are quantized to 16 bits, 8 bits, 4 bits, and 2 bits. So let's listen to these. Here's 16. That's a very high signal to noise ratio. It should sound essentially perfect. Here's 8 bits. You might be able to hear a little bit of noise in there. 4 bits, you should definitely hear some noise. And in fact, to my ear, I'm not only hearing noise, but I'm hearing some harmonic distortion. And that's because the rounding errors here are not truly random. They're repeating on every cycle of the sine wave. And here's 2 bits. Okay, and the 2-bit version is definitely introducing some audible harmonics into the sound. Now, here's a cello recording at 16 bits. And here's an 8-bit version. There's a 4-bit version where you might be able to hear noise more clearly. So notice that it's as if you hear the original sound in very high fidelity, just with some kind of uncorrelated noise added. Here's 2 bits. So a lot more noise in that example. Oh, so here's an answer to one of our questions again. What is the effect of rounding to the nearest integer sample value? Well, we've just learned the answer to that. The rounding effects can be approximated by adding white noise, or uniform random samples, of maximum amplitude of 1/2 of the least significant bit. So that means every time you add a bit, you get twice as many values, and so the amplitude of the rounding error cuts in half, and remember that a factor of 2 is about 6 decibels. So, in fact, the signal-to-noise ratio is about 6 dB times the number of bits, and plus there's a little constant factor of around 2. But basically you get 6 decibels per bit in integer samples. And how many bits per sample should we use, and why does it matter? Well, I think we can answer that now. The signal-to-noise ratio is determined by the bits per sample. If you want a particular high signal-to-noise ratio, to first approximation, just divide the signal-to-noise in dB by 6, and that tells you how many bits you need. Now, let's come to kind of summarize what we've learned. Can discrete samples really capture a continuous signal? And the answer is essentially yes. Discrete samples can capture a continuous band-limited signal without loss. That means if you have a band-limited signal, there are no lost frequencies, and to the extent that you can do perfect sampling, you have no noise. I think this is really an amazing theoretical result, that discrete samples can capture all of the information in a band-limited signal, even though that signal is continuous with time and effectively represents an infinite number of points and data. Somehow the fact that it's band-limited means that it cannot change infinitely fast, and therefore it doesn't really contain infinite amounts of information. The practical result number 1 is that sampling limits the bandwidth to 1/2 the sampling rate, which is called the Nyquist frequency. Practical result number 2 is sampling adds quantization noise, and the signal-to-noise ratio is about 6 dB per bit. Also, we learned what decibels are. You'll encounter those all the time, so that's important to know.